Welcome. Now, lean back and take a deep breath. Slowly let go of all the fatigue you've carried through the day. Because tonight, together, we'll drift gently into the quiet and peaceful embrace of the universe. Voyager 1 shut down its cameras forever. For the past 36 years, it has not captured a single new image. Today, it is the most distant human-made object ever built, traveling nearly 24 billion kilometers away from Earth. Even from that unimaginable distance, it still communicates with us and continues to send valuable scientific data from interstellar space. So why would a spacecraft that is still operating lose its ability to see? And if its cameras could somehow come back to life today, what would they actually show us? The story began in the early 1970s. Astronomers discovered that the giant planets were approaching an exceptionally rare alignment that happens only once every 176 years. A spacecraft launched at exactly the right time could use the gravity of each planet like a giant slingshot, gaining speed without carrying enormous amounts of fuel. NASA knew this opportunity would not come again for generations. Voyager 1 launched in 1977 with a clear objective: fly past Jupiter and Saturn and reveal these distant worlds in greater detail than ever before. The mission exceeded every expectation. It captured Jupiter's immense storms, Saturn's magnificent rings, and the thick atmosphere of Titan, changing our understanding of the outer solar system forever. Many of the iconic images still used in documentaries and textbooks were first returned by Voyager. But those achievements were only the beginning. As Voyager 1 left Saturn behind, it received one final gravitational boost that permanently changed its course. There would be no return. The spacecraft was thrown above the plane of the solar system and continued its journey into a region no human-made object had ever reached. Then, in 2012, it crossed one of the most important boundaries in the history of space exploration. Voyager 1 became the first spacecraft to enter interstellar space, leaving behind the region dominated by the Sun. Nearly 50 years after launch, it is still moving silently through the darkness. Yet the cameras that once revealed entirely new worlds were switched off long ago. The reason had nothing to do with failure. It was a decision made to keep the mission alive for as long as possible. To understand that decision, we first need to forget everything we know about modern cameras. Most people imagine Voyager carrying something similar to today's digital cameras. The reality was completely different. Voyager 1 launched in 1977. There were no smartphones, no digital cameras, no CCD or CMOS image sensors. Instead, Voyager used Vidicon camera tubes, a technology that closely resembled the imaging systems found in old television cameras. By today's standards, they were incredibly primitive. They could not capture a full-color photograph with a single shot. Whenever Voyager wanted to photograph a planet, it captured multiple black and white images through different color filters: green, blue, violet. Those separate images were later combined on Earth to create the color photographs we recognize today. The stunning images of Jupiter and Saturn were never taken as single-color pictures. They were carefully reconstructed from several individual exposures. Capturing the image was only the first challenge. Sending it back to Earth was even harder. Every photograph had to be converted into radio signals before beginning an unimaginably long journey across space. Today, Voyager is almost 24 billion kilometers away. At that distance, data travels back at an incredibly slow rate. A file that would reach someone across the world in seconds on modern internet connections would take many hours to arrive from Voyager. Even a tiny amount of data demanded enormous patience. A single image could require hours, and sometimes even days, to reach Earth depending on the transmission settings. Every photograph consumed precious time, precious energy, and precious bandwidth. Nothing could be wasted. Eventually, NASA's engineers faced a difficult choice. They could leave the cameras running and drain the spacecraft's remaining power within a few more years. Or they could permanently shut them down and dedicate every remaining watt to the scientific instrument still capable of exploring a region no spacecraft had ever visited before. By then, Voyager had already completed its planetary mission. There were no more giant planets waiting ahead. No bright rings. No colorful moons. Only the immense darkness between the stars. But while the cameras no longer had new worlds to photograph, the scientific instruments still had questions to answer. Where does the sun's influence truly end? What is the magnetic field like beyond the solar system? How do cosmic rays behave in interstellar space? Those questions became the new mission. Power made the decision unavoidable. Voyager was now far too distant for solar panels to be useful. Instead, it relied entirely on a radioisotope thermoelectric generator powered by the natural decay of plutonium. That power source slowly loses output every year. There is no way to recharge it. There is no replacement waiting in space. Every watt matters. The camera system alone required around 40 watts of power. That was simply too expensive for a spacecraft expected to survive for decades. So NASA made its choice. The cameras were switched off forever. But the shutdown went much further than flipping a simple switch. The software responsible for operating the cameras was completely erased from Voyager's tiny onboard memory. The freed memory was filled with new programs designed to support its scientific instruments. Even the heaters that protected the cameras from the extreme cold were turned off. For more than 3 decades, those cameras have remained frozen in temperatures below -50 degrees Celsius. Even if NASA wanted to activate them today, there would be no software to control them. No spare energy to power them. And no guarantee that the hardware itself could still function after spending decades in the unforgiving cold of interstellar space. Voyager's eyes were not closed by accident. They were sacrificed so the mission itself could continue. Now imagine something impossible. Suppose Voyager's power source suddenly became limitless. Its frozen hardware warmed up. Its missing software was restored. After decades of silence, the cameras opened once again. What would the first image actually look like? Most people expect something extraordinary. An unfamiliar star. A glowing nebula. Perhaps a completely unknown corner of the universe. After all, Voyager has already left the solar system. Surely the view must be dramatically different. In reality, the first image would probably disappoint almost everyone. It would appear almost completely black. Only a handful of faint stars would break the darkness. Nothing more. That may seem impossible. How could the most distant spacecraft ever built travel so far and still see almost nothing? The answer lies in the true scale of the universe. Movies often make space appear crowded with colorful clouds, bright galaxies, and breathtaking scenery around every corner. The real universe is nothing like that. Everything is separated by unimaginable distances. Even after traveling for nearly 50 years, Voyager has barely moved on the cosmic map. It has traveled an enormous distance by human standards. By the standards of the universe, it has only taken a tiny first step. So does that mean Voyager is surrounded by empty space? Not at all. It is actually passing through one of the most fascinating regions we have ever explored. Voyager has crossed the Heliopause. This is the boundary where the outward flow of charged particles from the Sun finally gives way to the environment of interstellar space. It is not a wall. It is not a sharp line. It is a vast transition zone where particles from the Sun constantly interact with material drifting between the stars. If human eyes could naturally see ultraviolet light, this seemingly empty region would look completely different. Scientists believe a structure known as the hydrogen wall exists near this boundary. As solar particles collide with interstellar hydrogen atoms, those atoms emit ultraviolet radiation. To us, the region appears completely dark. But in wavelengths invisible to human vision, it quietly glows. Unfortunately, Voyager's cameras were never designed to capture that light. Even if they still work perfectly today, they would never reveal that hidden glow. Despite the darkness, one object would still dominate the sky: the Sun. From Voyager's location, it no longer appears as the brilliant disk we see from Earth. Instead, it shines as an intensely bright star, far brighter than anything else in the sky. That creates another fascinating question. Could Voyager take one final photograph of Earth? The answer is almost certainly no. From nearly 24 billion kilometers away, Earth would appear so close to the Sun that separating the two would become extraordinarily difficult. Even if the camera had enough resolution, the Sun's overwhelming brightness would wash out our tiny planet. The famous pale blue dot image captured in 1990 was already an enormous technical challenge. Today, the task would be even more difficult. Earth would simply disappear into the Sun's glare. There is another problem few people consider. Voyager has spent more than 45 years traveling through space at incredible speed. During that time, microscopic dust particles and constant radiation have almost certainly affected its optics. Even if an image could somehow be captured, it would probably appear soft, scratched, and far from perfect. Many people also imagine that the stars would look completely different from Voyager's position. That seems reasonable at first. After all, it is almost 24 billion kilometers away from Earth. But once again, the universe reminds us how vast it truly is. The nearest star beyond the Sun is about 40 trillion kilometers away. Compared to that distance, Voyager has barely changed its viewpoint. The constellations would appear almost exactly as they do from Earth. The difference would be far too small for the human eye to notice. One day, Voyager's power source will finally become too weak to keep the spacecraft alive. Its scientific instruments will fall silent one by one. Eventually, its transmitter will send its final signal. Communication with Earth will end forever. But Voyager's journey will not. Long after every system has gone silent, it will continue drifting through interstellar space. Locked inside is a small golden record carrying sounds, music, greetings, and the story of humanity. A silent message from one small world, traveling endlessly through the darkness between the stars. Hubble has transformed our understanding of the universe in countless ways. It helped measure the expansion rate of the universe with unprecedented precision. It provided compelling evidence for the existence of supermassive black holes. Yet some of its greatest discoveries were completely unexpected. One of the most remarkable was the study of planets beyond our own solar system. When Hubble was launched, we had no idea how many worlds orbited distant stars. The ability to analyze the atmosphere of an exoplanet from a telescope orbiting Earth was once almost unimaginable. Today, it is one of Hubble's greatest scientific achievements. Scientific discoveries are often measured by how deeply they influence future research. When astronomers publish an important result, other scientists build upon it. The more often a discovery is referenced, the greater its impact. But science is not measured only by numbers. Some discoveries capture the imagination of millions. They change the way humanity sees its place in the universe. That is exactly what Hubble has done. For many astronomers, choosing a favorite Hubble discovery is almost impossible. Some point to the Orion Nebula. When Hubble observed this vast stellar nursery, astronomers found something extraordinary. Around many young stars, they could clearly see disks of gas and dust. These were protoplanetary disks, the places where new planetary systems were beginning to form. The evidence was sitting right in front of them. Seeing those disks for the first time was unforgettable. It was one of those rare moments when every piece of the puzzle suddenly fell into place. The images revealed something no human being had ever witnessed before. Others remember the moment Hubble observed a galaxy known as NGC 4261. Near its center, astronomers discovered a remarkably small disk of gas and dust. By measuring the motion of that gas, they calculated the mass of the invisible object hidden inside. The result provided some of the strongest evidence yet for a supermassive black hole. For many researchers, however, Hubble's greatest gift was beauty itself. Massive galaxy clusters bend the light from even more distant galaxies. This effect, known as gravitational lensing, creates enormous arcs of light across space. Red galaxies. Blue background galaxies. Light stretched and curved by gravity itself. The images are scientifically priceless. They are also breathtaking. Before Hubble, many astronomers believed galaxies in the distant universe would simply be too faint to observe. Instead, Hubble revealed that even the earliest galaxies contained bright regions where stars were rapidly forming. those young stars made the galaxies visible across astonishing distances. As a result, Hubble allowed us to observe objects whose light began its journey when the universe was only 700 or 800 million years old. Today, the universe is nearly 13.8 billion years old. Looking through Hubble is like opening a window into cosmic history. Instead of seeing space as it is today, we watch galaxies growing, changing, and evolving billions of years in the past. Many astronomers are especially fascinated by Hubble's colorful images of enormous clouds of gas and dust. These clouds are beautiful on their own, but they also hide something even more extraordinary. Inside them, new stars are being born. Visible light cannot easily penetrate these dense clouds. Infrared observations reveal what lies hidden within. Each new image exposes another generation of stars emerging from the darkness. Some researchers devoted years to studying regions such as NGC 346, watching young stars shape the surrounding clouds. Watching powerful radiation carve enormous structures into interstellar gas. Every image revealed something new. Even after years of studying the same region, the excitement never disappeared. That constant sense of discovery is what made Hubble unlike any telescope before it. After decades in orbit, Hubble has produced more unforgettable moments than almost any scientific instrument in history. For some astronomers, one image stands above the rest. The first direct optical images of an exoplanet orbiting another star. For others, it was the Bullet Cluster, a collision between two galaxy clusters that provided powerful evidence for the existence of dark matter. And for many scientists, one of Hubble's greatest achievements was refining the value of the Hubble constant. By measuring the expansion rate of the universe with unprecedented accuracy, the telescope fulfilled one of the primary goals it had been built to achieve. One of Hubble's most spectacular targets lies far beyond the Milky Way. The Large Magellanic Cloud is a small companion galaxy orbiting our own. Although it appears as nothing more than a faint patch of light to the naked eye from the southern hemisphere, it contains some of the most active regions of star formation ever observed. Among them is the Tarantula Nebula. Hubble revealed this extraordinary region in remarkable detail. It exposed one of the most energetic stellar nurseries in the nearby universe. Inside the nebula, enormous clouds of gas and dust are constantly shaped by powerful young stars. Radiation and stellar winds carve vast cavities through the surrounding material, creating intricate structures that stretch across light-years of space. One particularly active region contains the supernova remnant NGC 2060. What remains today is the aftermath of a massive star that ended its life in a violent explosion. The expanding clouds of gas are all that is left of that ancient catastrophe. At the center, the collapsed core survived as a rapidly spinning neutron star, a pulsar. The brilliant glow of the Tarantula Nebula comes from hydrogen gas energized by newborn stars. Their intense ultraviolet radiation strips electrons away from hydrogen atoms. As those electrons recombine, the gas begins to shine with vivid shades of red and green. The light is so powerful that the Tarantula Nebula can even be seen with the naked eye despite being nearly 170,000 light-years away. Yet the brightest stars in the region extend beyond Hubble's field of view. Wider observations from ground-based observatories reveal the nebula's true scale. At its center lies R136, an extraordinarily dense star cluster containing some of the most massive stars ever discovered. For many years, astronomers debated whether the intense light from this region came from a single gigantic star or from an entire cluster. Only detailed observations finally revealed the truth. The brightness came from an enormous collection of massive young stars packed into an incredibly small volume of space. The Tarantula Nebula is also home to supernova 1987A. It remains the closest supernova observed since the invention of the telescope. For astronomers, it became a once-in-a-lifetime opportunity to watch the aftermath of a stellar explosion unfold in real time. The Tarantula Nebula remains one of the largest and brightest stellar nurseries ever observed. It continues to be one of the most fascinating objects in the night sky. More than 4 centuries before Hubble entered orbit, another telescope changed astronomy forever. In 1609, Galileo Galilei introduced his telescope to the people of Venice. Only a few months later, he discovered 4 moons orbiting Jupiter: Io, Europa, Ganymede, and Callisto. His observations proved that not everything revolved around Earth. 400 years later, another telescope would once again reshape humanity's view of the universe. Scientists gathered in Venice to celebrate Hubble's discoveries and discuss the future of astronomy. When Hubble launched in 1990, a new era of exploration began. Its story, however, is about far more than science. It is also a story of engineering, politics, international cooperation, and thousands of people determined to accomplish something that had never been attempted before. From the very beginning, difficult decisions shaped the project. Budget limitations forced engineers to redesign parts of the telescope. The original mirror was planned to be larger. To reduce costs, its diameter was lowered to 2.4 meters. Even that compromise demanded years of extraordinary engineering. At the same time, political pressure continued to grow. Costs increased. Support became uncertain. NASA was encouraged to seek international partners capable of sharing both the financial burden and the technical challenges. That partnership eventually came through the European Space Agency. The collaboration proved essential. It strengthened political support and helped keep the project alive during some of its most uncertain years. Without that international effort, Hubble might never have reached space. Despite surviving years of political uncertainty, Hubble faced its greatest challenge only after reaching orbit. Soon after launch, astronomers noticed something was terribly wrong. The telescope could not focus properly. The images were blurred. Instead of the sharp views everyone had expected, scientists struggled to extract even basic details from the observations. For the teams who had spent years building the telescope, the discovery was devastating. For weeks, engineers searched for the cause. Every possibility was examined. Eventually, they found the answer: a tiny flaw in Hubble's primary mirror. The error measured only a fraction of the width of a human hair. Yet it was enough to affect every image the telescope produced. Fortunately, Hubble had been designed with one remarkable advantage. It could be repaired in space. Astronauts would not simply visit the telescope. They would perform delicate surgery hundreds of kilometers above Earth. Over the years, 5 servicing missions restored and upgraded Hubble. Each mission demanded extraordinary precision. Working in bulky spacesuits while handling some of the most sensitive scientific instruments ever built left almost no room for mistakes. Among astronauts, one rule mattered above all others. Do not damage the telescope. Every bolt, every cable, every instrument had to be handled with extreme care. For scientists, the spectacular images were the ultimate reward. For the astronauts, those same images meant something equally important. They proved the repairs had succeeded. One of the most challenging servicing missions took place in 2009. Astronauts replaced aging instruments and installed powerful new cameras. The work required movements so precise that many compared the operation to performing brain surgery in orbit. Tiny screws, fragile connectors, complex electronics. Everything had to function perfectly. Back on Earth, engineers waited anxiously for the first test results. The moment the new systems powered on, the tension inside the control room was overwhelming. Then the first data arrived. The repairs had worked. Not only had Hubble been restored, it had become more capable than ever before. Those exhausting missions extended the telescope's life by many years and opened the door to discoveries that would have been impossible otherwise. As remarkable as Hubble had become, astronomers were already looking toward the future. They dreamed of a telescope capable of seeing even farther into space. One that could detect objects too faint and too distant for Hubble to observe. The first galaxies. The first stars. The earliest planetary systems. The atmospheres of worlds orbiting distant suns. Hubble had already transformed astronomy. But it had also revealed how much of the universe still remained beyond our reach. When Hubble launched in 1990, astronomers expected groundbreaking science. Few imagined it would become a cultural icon recognized around the world. Its photographs reached far beyond scientific journals. They inspired artists, musicians, designers, filmmakers. Some of its most famous images appeared on album covers, in movies, and in video games. Others became paintings, sculptures, and even tattoos. Hubble changed not only the way scientists viewed the universe. It changed the way millions of people imagined it. Its images became symbols of curiosity itself. Even professional observatories celebrated Hubble's achievements. During the 50th anniversary of the Lovell telescope, one of Hubble's famous images was projected across the enormous radio dish. For a single night, one of the world's largest telescopes became an outdoor cinema dedicated to the exploration of the cosmos. It was a tribute not only to Hubble, but to humanity's endless desire to understand the universe. Every telescope observes the universe in a different way. Each part of the electromagnetic spectrum reveals something unique. Visible light shows stars and galaxies. Infrared light uncovers objects hidden behind thick clouds of dust. X-rays expose the most violent events in the cosmos. No single telescope can tell the entire story. That idea inspired one of astronomy's most ambitious observing campaigns. The project became known as GOODS, the Great Observatory's Origins Deep Survey. Its goal was simple in concept but extraordinary in execution. Point the world's most powerful telescopes toward the same tiny region of the sky. Then combine everything they observed into one complete picture of the universe. Hubble was one of the key instruments. But it was far from alone. The Very Large Telescope in Chile, the Spitzer Space Telescope, the Chandra X-ray Observatory, and several other observatories all focused on exactly the same distant galaxies. Each telescope contributed a different piece of the puzzle. Together, they allowed astronomers to reconstruct billions of years of cosmic history. The deeper a telescope observes, the fainter the objects it can detect. Long exposures reveal galaxies that would otherwise remain invisible. But depth alone is not enough. Different wavelengths reveal completely different physical processes. Only by combining observations across the electromagnetic spectrum can astronomers truly understand how galaxies formed and evolved. This was the foundation of the GOODS project. Hubble had already demonstrated the incredible power of deep observations years earlier. One of its most famous images became known as the Hubble Deep Field. The telescope stared at an area of sky so small it seemed almost empty. Yet when the image was finally processed, thousands of galaxies appeared. What had looked like darkness was actually filled with entire island universes. The GOODS survey expanded that idea dramatically. Instead of studying a tiny patch of sky, astronomers observed much larger regions with far greater sensitivity. The result was one of the most detailed maps of the distant universe ever created. Ground-based telescopes spent hundreds of nights collecting visible and infrared light. Hubble repeatedly returned to the same fields over many months. Rather than observing everything at once, it spread the exposures across time. That strategy allowed astronomers to discover distant supernovae and measure how the expansion of the universe has changed over billions of years. Those observations provided some of the strongest evidence for dark energy. Spitzer added another critical layer. Its infrared detectors revealed galaxies hidden behind enormous clouds of cosmic dust. Many of these systems were actively forming stars but remained almost invisible in ordinary light. Infrared observations exposed them for the first time. Meanwhile, the Chandra X-ray Observatory searched the same regions for high-energy radiation. It discovered hundreds of powerful X-ray sources. Many of them were supermassive black holes feeding on surrounding gas deep inside young galaxies. Each observatory revealed something the others could not. Together, they created one of the most complete views of the distant universe ever assembled. Understanding those galaxies required one more crucial measurement: distance. As light travels across the expanding universe, its wavelength stretches. The farther the galaxy, the greater this stretching becomes. Astronomers call this effect redshift. By measuring a galaxy's redshift, they can determine how far away it is and how long its light has traveled through space. Thousands of galaxies inside the GOODS fields had their redshifts measured with extraordinary precision. Those measurements allowed astronomers to place each galaxy at its proper location in cosmic history. Instead of a flat image, the universe became a three-dimensional timeline stretching back billions of years. Some galaxies gathered into enormous clusters. Others formed vast filaments extending across millions of light-years. Patterns that were completely invisible before suddenly emerged. The Good Survey became one of the richest astronomical archives ever created. Researchers have already published hundreds of scientific papers based on its observations. Even today, new discoveries continue to emerge from the same data. Future observatories will keep returning to these regions of the sky. Every new generation of telescopes will see a little farther, a little deeper, and reveal another chapter in the history of the universe. In 2009, astronauts returned to Hubble for one of the most ambitious servicing missions ever attempted. Their goal was not simply to repair the telescope. They were about to transform it. One of the most important upgrades was the installation of Wide Field Camera 3, better known as WFC-3. This instrument would dramatically expand Hubble's ability to observe the universe. Unlike previous cameras, WFC-3 could study the cosmos across a much broader range of wavelengths, from ultraviolet light to visible light and deep into the infrared. It became one of the most versatile scientific instruments ever placed aboard the telescope. Compared to its predecessor, WFC-3 produced sharper images, detected much fainter objects, and collected far more light. But its greatest strength was its infrared capability. Infrared astronomy allows scientists to study objects that are almost invisible in ordinary light. Cold clouds of gas, young stars hidden inside thick dust, the earliest galaxies in the universe, all become much easier to detect at infrared wavelengths. Visible light struggles to pass through dense clouds of cosmic dust. Infrared light can travel much farther, revealing structures that would otherwise remain completely hidden. For decades, Hubble amazed the world with breathtaking images of colorful nebulae. Yet astronomers always wanted to know what was happening inside those clouds. Infrared observations finally revealed the answer. Entire generations of newborn stars appeared where visible images had shown only darkness. Before WFC-3, Hubble relied on an older infrared instrument with a much smaller detector. Its field of view was limited. Its images covered only a tiny portion of the sky at one time. Scientists often faced a difficult choice: observe a wide area with little detail, or study a small region with much greater precision. WFC-3 removed that compromise. Its detector contained nearly 1 million pixels, roughly 15 times more than the previous infrared camera. Astronomers could now capture larger regions of space without sacrificing detail. The improvement was extraordinary. More sky, sharper images, greater sensitivity. Those advances allowed Hubble to detect galaxies even farther away than before. This was especially important for studying the early universe. As the universe expands, light traveling across billions of years is stretched into longer wavelengths. The farther away an object is, the more its light shifts toward the red end of the spectrum. Eventually, visible light becomes infrared light. Without infrared observations, many of the oldest galaxies would remain completely invisible. WFC3 opened a new window into that distant era. One of its most famous achievements came from a tiny patch of sky already known as the Hubble Ultra Deep Field. The original observations had already revealed thousands of distant galaxies. But when WFC3 observed the same region in infrared light, even more galaxies appeared. Some were so distant that their visible light had been stretched entirely into infrared wavelengths. For the first time, astronomers could observe galaxies whose light began its journey more than 13 billion years ago. They were seeing the universe when it was only about 5% of its current age. Every one of those faint galaxies carried information from a time when the first generations of stars were beginning to shape the cosmos. Studying them helps astronomers test theories of galaxy formation and understand how the modern universe came to exist. Each new observation pushes us a little closer to answering one of humanity's oldest questions. How did everything begin? Hubble's discoveries did not end with distant galaxies. Its new instruments also transformed the way astronomers study nearby galaxies and regions where stars are still being born. One of the most remarkable examples is the Large Magellanic Cloud. This neighboring galaxy has become one of the most important natural laboratories for understanding stellar evolution. Because it lies relatively close to the Milky Way, Hubble can resolve individual stars instead of seeing only a blurred cloud of light. That level of detail allows astronomers to follow the entire life cycle of stars. From their birth inside dense clouds of gas to their final stages billions of years later. One of Hubble's largest panoramic images focused on an enormous star-forming region within the Large Magellanic Cloud. The image revealed countless clouds of glowing gas intertwined with massive clusters of young stars. It quickly became one of the most detailed portraits of stellar birth ever created. The Large Magellanic Cloud has fascinated observers for centuries. Sailors crossing the southern hemisphere used it as a familiar landmark in the night sky. Although it now carries the name of Ferdinand Magellan, the galaxy had already been recorded long before his voyage. Persian astronomer Abd ul-Rahman al-Sufi described it centuries earlier. Other explorers also documented its existence before it became widely known in Europe. Today, the Large Magellanic Cloud remains one of the most valuable objects in modern astronomy. It offers an extraordinary opportunity to study star formation at a level of detail impossible in more distant galaxies. Every bright cluster, every cloud of glowing hydrogen, every newborn star adds another piece to the story of how galaxies evolve over time. Hubble continues to reveal structures that earlier generations of telescopes could barely detect. Its observations show that star formation is far more dynamic than astronomers once believed. Massive stars reshape their surroundings through intense radiation and powerful stellar winds. Shock waves compress nearby clouds. New generations of stars begin to form. Those young stars eventually repeat the same cycle. The process continues for millions of years, slowly transforming an entire galaxy. By studying nearby regions like the Large Magellanic Cloud alongside galaxies billions of light-years away, Hubble allows astronomers to compare the present with the distant past. The telescope has shown that the same physical laws governing star formation today have been shaping the universe since its earliest history. Across billions of years and unimaginable distances, the cycle of creation has never truly stopped. Every new observation strengthens one remarkable idea. The universe is constantly changing. Stars are born. Stars die. Galaxies grow. And every generation leaves behind the raw material for the next. That endless cycle is one of the greatest stories Hubble has ever revealed. For more than 3 decades, Hubble has changed the way humanity looks at the universe. Every new generation of instruments has expanded its reach. Every servicing mission has extended its life. Every observation has answered old questions while raising even bigger ones. No one expected the telescope to remain productive for so many years. Yet it continues to push the boundaries of modern astronomy. Its greatest achievement is not a single image or one remarkable discovery. It is the enormous body of knowledge built from millions of observations. Every photograph is far more than a beautiful picture. Each one contains measurements of distance, temperature, chemical composition, motion, age. Together, they tell the story of how the universe has evolved across billions of years. Hubble has measured the expansion of the cosmos, observed planets orbiting distant stars, revealed supermassive black holes hidden inside galaxies, captured stars as they were born, and witnessed the final moments of stars reaching the end of their lives. Few scientific instruments have contributed so much to so many different fields of astronomy. Its success also shaped the future. Every lesson learned from Hubble influenced the design of the telescopes that followed. New observatories were built to see farther, to observe fainter objects, to detect wavelengths Hubble could never reach. The search continues with even more powerful instruments. Astronomers hope to witness the first stars igniting after the Big Bang, study the atmospheres of distant worlds in extraordinary detail, and uncover galaxies that have remained hidden since the beginning of cosmic history. Yet none of those future discoveries would exist without Hubble. It proved that placing a telescope above Earth's atmosphere could completely transform astronomy. It inspired generations of scientists, engineers, and dreamers. When Hubble launched in 1990, astronomers expected an extraordinary scientific instrument. Very few imagined it would become one of the greatest symbols of exploration in human history. Today, its images appear in classrooms, museums, books, films, music, art, and in the minds of millions of people who have looked up at the night sky and wondered what lies beyond. Long after Hubble completes its final observation, its legacy will continue. Every telescope that follows will stand on the foundation it created. Every new discovery will carry a small part of its story. Because Hubble did far more than photograph the universe. It changed the way humanity sees its place within it. Hubble's story is still being written. Even after decades in orbit, its observations continue to shape modern astronomy. Every year, scientists return to its vast archive in search of answers to new questions. Many of its greatest discoveries were never part of the original mission. They emerged because the telescope was capable of seeing farther and with greater precision than anyone had imagined. Its images have revealed galaxies from the early universe, captured the birth of stars inside hidden clouds of dust, measured the expansion of space with extraordinary accuracy, and uncovered planets orbiting distant suns. Each discovery has become another piece of a much larger picture, one that continues to evolve with every observation. Perhaps Hubble's greatest achievement is not any single photograph. It is the perspective it has given humanity. For thousands of years, the night sky appeared silent and unchanging. Hubble showed us a universe in constant motion. Stars are born inside enormous clouds of gas. They shine for millions or billions of years. Eventually, they explode, enriching space with the elements needed to create new stars and new planets. Galaxies collide. Black holes shape entire stellar systems. The universe is not still. It is alive with change. Every image reminds us that we occupy only a tiny corner of an unimaginably vast cosmos. Yet from that tiny corner, humanity has built instruments capable of looking billions of years into the past. Every distant galaxy captured by Hubble is more than a collection of stars. It is a message sent across time. A glimpse of the universe as it once was. As new observatories continue the search, Hubble remains one of the greatest scientific achievements ever placed into orbit. Its discoveries will continue inspiring future generations of astronomers. Its images will continue reminding us how much remains unexplored. Because every answer Hubble has given us has led to another question. And every new question carries us one step deeper into the universe. For centuries, the Large Magellanic Cloud has attracted the attention of astronomers. Its brightness makes it one of the easiest neighboring galaxies to observe from the southern hemisphere. Although it is commonly associated with Ferdinand Magellan, the galaxy was documented long before his famous voyage. Persian astronomer Abd al-Rahman al-Sufi described it centuries earlier. Other explorers also recorded its existence before it became widely known throughout Europe. Its familiar name reflects history rather than discovery. Today, the Large Magellanic Cloud remains one of the most valuable regions in the sky for astronomical research. Its proximity allows Hubble to resolve individual stars with extraordinary clarity. Instead of seeing a distant blur, astronomers can study stellar populations one star at a time. That level of detail provides an unparalleled opportunity to understand how stars form, evolve, and eventually die. Massive young stars illuminate enormous clouds of hydrogen. Powerful stellar winds sculpt pillars of gas stretching across light years. Shock waves from ancient supernovae compress nearby clouds, triggering the birth of entirely new generations of stars. Every observation reveals another chapter in the ongoing story of stellar evolution. Because the Large Magellanic Cloud is close enough to examine in remarkable detail while remaining large enough to contain every stage of stellar life, it serves as a natural laboratory unlike any other. The processes unfolding there today are the same ones that have shaped galaxies across the universe for billions of years. By comparing nearby stellar nurseries with galaxies at the edge of the observable universe, astronomers can piece together the history of cosmic evolution. Hubble has shown that the universe follows the same fundamental laws everywhere we look. Whether inside a neighboring galaxy or billions of light-years away, stars are born from collapsing clouds of gas. They spend millions of years producing light and heavier elements. Eventually, many of them return that material to space, providing the ingredients needed for future generations of stars and planets. It is an endless cycle of creation and renewal. Every new observation strengthens that picture. Every image reveals another small piece of an unimaginably vast universe. And with each discovery, Hubble continues to remind us that even our closest galactic neighbors still hold countless mysteries waiting to be explored. For astronomers, the Large Magellanic Cloud is far more than a neighboring galaxy. It is one of the best places in the universe to watch the life cycle of stars unfold. Because it lies relatively close to the Milky Way, Hubble can distinguish individual stars with remarkable precision. That level of detail allows scientists to study stellar evolution from beginning to end. Massive clouds of hydrogen collapse under gravity. Newborn stars ignite deep inside the darkness. Their powerful radiation slowly pushes away the surrounding gas, revealing brilliant clusters that continue to shape their environment. The process repeats across millions of years. Each generation of stars leaves behind the material needed for the next. Observing these regions helps astronomers answer some of the oldest questions in astronomy. How do stars form? How do galaxies evolve? How did the universe come to look the way it does today? Every new observation brings another piece of the answer. The Large Magellanic Cloud has become one of the most intensively studied galaxies in the sky. Its importance extends far beyond its beauty. It serves as a bridge between nearby stellar nurseries and the distant galaxies observed in the early universe. By comparing both, astronomers can trace how star formation has changed across billions of years of cosmic history. Hubble has shown that the same physical laws operate everywhere. The birth of a star inside the Large Magellanic Cloud follows the same fundamental processes as the birth of stars in galaxies billions of light-years away. Gravity gathers gas. Nuclear fusion begins. Light fills the surrounding darkness. Eventually, those stars enrich space with heavier elements that become the building blocks of future worlds. It is a cycle that has repeated for almost the entire history of the universe. With every new observation, Hubble continues to refine that picture. Its discoveries remind us that even the closest galaxies still contain countless mysteries waiting to be explored. Every image carries new information. Every observation opens another path toward understanding our cosmic origins. And with each passing year, Hubble continues to prove that the universe is far richer, more complex, and far more beautiful than anyone once imagined. The story of the universe is written in light. Every photon captured by Hubble has traveled an incredible distance before reaching the telescope. Some left their galaxies only a few million years ago. Others began their journey more than 13 billion years in the past. By collecting that ancient light, Hubble allows us to look backward through cosmic history. The farther we look into space, the farther we look into time. This simple idea has transformed modern astronomy. Galaxies that appear as tiny points of light are not being observed as they exist today. They are seen as they were billions of years ago. Some belong to a time when the universe was still in its infancy. Others reveal the first generations of stars beginning to illuminate the darkness after the cosmic dark ages. Every observation adds another frame to the story of how structure emerged from an expanding universe. As technology continues to improve, astronomers are pushing that boundary even farther. Each new generation of telescopes extends humanity's vision deeper into space. Each new observation uncovers objects that once seemed permanently beyond our reach. Hubble laid the foundation for that progress. Its discoveries inspired more advanced observatories designed to explore wavelengths beyond its capabilities and detect galaxies even older and fainter than those Hubble revealed. Yet despite these advances, Hubble remains one of the most productive scientific instruments ever built. Its archive contains millions of observations that researchers continue to analyze decades after they were first collected. New discoveries still emerge from data recorded years ago. Questions that did not even exist when the observations were made are now being answered using the same images. That is one of Hubble's greatest strengths. Its mission did not end when a photograph was taken. Every image became a permanent scientific record that future generations could study in ways the original observers never imagined. Few scientific projects have left such a lasting impact. Hubble changed astronomy. It reshaped our understanding of the universe. And perhaps most importantly, it reminded humanity that every answer leads to another question waiting somewhere in the darkness beyond. Every generation has looked toward the night sky and asked the same question. How far does the universe really extend? For centuries, the answer remained beyond our reach. Then Hubble changed everything. It revealed galaxies where we once saw only darkness. It measured distances that had never been measured before. It captured light that had been traveling across the universe for billions of years. Every observation expanded the limits of human knowledge. Yet Hubble also taught us something unexpected. The farther we look, the more mysteries we discover. Every answer leads to another question. Every new image hints at objects even farther away. Galaxies become smaller, older, fainter, until they disappear beyond the limits of the telescope itself. Those limits inspired the next generation of observatories. Engineers began designing telescopes capable of seeing deeper into infrared wavelengths, powerful enough to study the first galaxies, sensitive enough to analyze the atmospheres of distant planets, precise enough to search for the earliest structures that formed after the Big Bang. Hubble became the foundation for everything that followed. Its discoveries shaped the questions future telescopes would attempt to answer. Even today, astronomers continue returning to Hubble's enormous archive. Many observations collected years ago are still producing new discoveries. As analysis techniques improve, old data often reveals details that were impossible to recognize when the images were first taken. That is one of Hubble's greatest legacies. Its mission continues long after the moment each photograph is captured. Millions of observations remain available for future generations of scientists. Each one contains information waiting to be explored. Very few scientific instruments have influenced humanity as deeply as Hubble. It transformed astronomy from the study of isolated objects into the study of cosmic history itself. For the first time, humanity could watch galaxies evolve across billions of years. Witness the birth of stars. Measure the expansion of the universe. And observe worlds orbiting distant suns. Hubble did more than expand our knowledge. It expanded our imagination. It reminded us that no matter how much we discover, the universe will always be larger than our understanding. And perhaps that is its greatest achievement. Not that it answered every question, but that it inspired humanity to keep searching.